with international teams, mainly from USA, Saudi Arabia, Turkey, Italy, Hungary, and United Kingdom. So before we starting, I just want to take you through an introduction of my career path. So I have obtained my my bachelor degree in general chemistry from Lebanese University in Beirut. Then I got my master's degree in molecular chemistry from the same university, and another master's degree in organic chemistry from Beirut and Po University in France. In 2014, I joined King Abdullah University of Science and Technology to pursue my PhD studies, and I have achieved my PhD degree in chemical science with the main work on developing porous materials for gas separation. I've spent 2.5 years as a postdoc in King Abdullah University working on developing porous polymers for different type of applications that I'm going to share most of these applications with you today. And currently I'm a research faculty at College of Petroleum Engineering and Geoscience in Dhahran. So for those who are not really expert in polymers, we're going to go through a little bit of definitions of polymers and classification of polymers. So polymers are defined as a sustainable, as a substance or materials consisting of large molecular weights or macromolecules and composed of many repeating units. So we use polymers in our daily life. So every one of us use polymers and we see it around us. So here are just a few examples on the polymers that we see around, like plastic bags, different type of paints, cups, clothes, and there are plenty of different type of polymers. We see it in our computers, in printers, in desks, in phones, anywhere. So polymers exists everywhere. Based on their application and their performance, polymers have been classified into 4 main categories. So we have standard polymers that is for general use, and this is like one of the first type of polymers that have been developed with low thermal and chemical stability, such as high density polyethylene, low density polyethylene, and polymethyl methacrylates. We have another type of polymers named as engineering polymers, which kind of for daily use applications, nylon, polycarbonates, and acrylic acids, for example. A more advanced type of polymers, it's called high performance polymers. This is considered as a stable polymers and have been produced on large scale by industry and tested for various type of applications, such as PEEK, which is referred to polyether ketone, polysulfone, and polyvinylene difluoride. Nowadays, there is a new generation of polymers. It's called ultra high performance polymers. So this one is still under investigation and studied, and some of these polymers has came out as a commercialized material. It owns high thermal stability, high mechanical properties, such as polyimides, polybenzoimidazole, and polymers of intrinsic microporosity. So before going to polymer of intrinsic microporosity, I want to share with you the 5 main types of porous polymers that have been taken into consideration for industrial applications. So porous materials has been categorized in many different types, and these are the 5 most common ones. This material is called zeolites. It's known for its crystallinity. It's a crystalline inorganic materials. Then we have another type of crystalline organic materials. It's called metal organic frameworks. This material is built up from organic ligands and metals, and it has a high crystallinity and well-ordered pore distribution. We have COFs, which is referred to covalent organic frameworks, which is also prepared from crystalline organic materials. We have silica, and this is considered as amorphous inorganic materials. And we have PIMs, which is polymers of intrinsic microporosity. So PIMs also has been classified based on the polymer chain and the rearrangements. We have 3 main types of PIMs. The first one is linear polymer, where the chains is linear. So as you can see here, it's just a linear polymer. And this type of polymer is solution processable. So you can dissolve it in organic solvents. You can convert it to films or different type of materials. A few examples on this, like the well-known type of linear polymers, is polyacetylenes and polyamides. Another type of polymers is called ladder polymer, and this is also a solution processable polymer. Ladder is built like ladder-like, so it's more rigid than this type of polymer, and it has a higher rigidity, and this helps later on to develop higher porosity when it comes to developing porous polymers. And the last type of this polymer is network polymer. This type is known as cross-linked polymer, so it's insoluble in organic solvents, such as tryptophan-based material. So you can see here the monomers or the units are connected through cross-linking, and that's why it becomes insoluble. This type of polymers cannot be prepared as membranes for any application, but it can be used as sorbents in its powder format. Coming to the applications, so PIMs have been investigated intensively in the last decade. The main focus was developing PIMs or porous polymers for gas separation applications and the storage. So it has been used in different formats, in membranes, as adsorbents as well, for natural gas sweetening. So natural gas sweetening is referred to the separation of carbon dioxide from methane. Air separation is to separate oxygen from nitrogen, and olefin paraffin separation. Recently, there is an interest in developing PIMs for organic solvent nanofiltrations, such as like for dye removal, pharmaceutical applications, and water treatment as well. And there is also focus on developing PIMs for water oil purification or water separation from oil. So these kind of emerging technologies that they're trying to use porous polymers in it. And this one is very recent, where we developed type of polymers where we have used these PIMs polymers to encapsulate nanocrystals and enhance solubility. And this is not related to the oil field, but it has a very potential in electronics as well. Now, I just want to show you what PIM preparation look like and how we can achieve or prepare a porous polymer. So simply to have a porous polymer, you have to have something called kinked structure. So if we look at this one, I'm not sure how much you're familiar with the chemistry and the organic chemistry. So benzene ring is considered as a flat ring. So if you have a flat ring, when you make a polymer out of this, you get a very linear polymer. So imagine you have more than a chain of a linear polymer, then the packing on the top of these chains will be very tight. So you won't have any porosity between the chains. So thus, we need something called kinked unit. So kinked unit mainly is non-planar unit. This is one of the main or most used examples here. It's called the spirobisindane unit. So it has a spirocenter here. And the presence of this kinked unit allows the formation of a porous polymer. And these are the first prepared polyimides-based polymers for gas separation applications. So once you have this polymer, there is a protocol to follow to prepare a membrane for gas separation. So first it starts with dissolving your polymer in a proper solvent like a chloroform or dichloromethane or even polar aprotic solvents such as DMF or NMP. Then you filtrate your polymer and you cast in a flat Petri dish and you let it evaporate under specific kind of temperature, maybe room temperature, or even you need to heat a little bit to remove the solvent. And you end up having this kind of membrane. So this is known as a dense membrane with a thickness usually ranges between 30, 40 up to 100 micrometers. The mechanism of gas separation is very simple. So it has 3 stages: sorption, diffusion, and desorption. So imagine this is your membrane, this red box. Then you have, let's say, carbon dioxide and methane on this side. So these gases, this mixture of gases will approach the surface of the membrane by applied pressure here. And it will get absorbed and on the surface and then diffuse through the membrane to get from the other side. And from the other side, you will see like you have some favored sorption over others. Like you could see, for example, CO2 will go faster than methane. And the reason behind this is depending on permeability. So permeability of a gas is a factor of diffusivity and selectivity and solubility. So diffusivity is a kinetic diameter that is governed by the molecular size of the gas. So when we talk about carbon dioxide and methane, we know carbon dioxide has a kinetic diameter of 3.3 angstrom. However, methane has a kinetic diameter of 3.64 angstrom. So these type of polymers, porous polymer, can distinguish up to this level, like in the angstrom level, where it can allow the separation happens. And also this diffusivity is depending on size sieving properties and the chain mobility. So when we talk about the chain mobility here, we mean the configuration of the structure of the polymer chains, how it's connected and how it's packing on the top of each other. And the other factor is solubility. Solubility is a thermodynamic factor depending on the condensability of the gas and on some specific chemical interactions that could happen between the gas and the polymer chains. So once we achieve a permeability of a specific gas, then we plot it on this curve. This is known as a Robinson trade-off plot, where you plot your permeability and selectivity, and you see your performance compared to what have been reported in literature or what have been existing as a commercially available materials. So this was like the 2000 trade-off curve, and researchers have been focusing on going to a different desired performance area, which is here, where you can achieve very high permeability and at the same time very high selectivity. So to reach this area, we have to better understand the structure property relationship between the polymers and the gases. And this was my major focus in my PhD studies. And I'm going to show you like a few case studies where we have investigated the effect of function groups and and check the performance and what this function group could affect in terms of gas separation. So taking the first case, there is a unit here. It's very known for the people who works with polymers and especially for gas separations. This unit is a kinked unit. So it is not a planar. So when I see kinked, it's not a planar. It's not benzene ring. You can see it has a torsion angle of 120 degrees. So it's like V-shaped. So when we grow a polymer out of this, so imagine many V-shapes connected to each other and another chain with many V-shapes connected to each other. So underneath you will see a space. So there is kind of empty space in between, and this is responsible to generate porosity. So we wanted to know what is the effect of this nitrogen. Is it doing anything that is useful for gas separation, or it just stick there because we have this molecule? So we thought of designing the same exact structure but replacing nitrogen atom with carbon atom, and we came up with carbocyclic Troger base. So carbocyclic Troger base had a little slightly less torsion angle. So when we did the porosity measurement, we use a technique called BET surface area measurement, where you can evaluate the porosity of your polymers or porous materials. So we found that the polymer that is made with this nitrogen-based unit has a BET surface area of about 500. However, when we replace the nitrogen unit with carbon, the BET surface area goes even higher, like around 50% higher. So there is a big change that is happening due to the presence of nitrogen. So now back to the previous slide, if this change going to be because of diffusivity or because of solubility. So we did another study and we found that there is no interactions happening between nitrogen and carbon dioxide, but there is interactions going on between the nitrogen atoms inside the polymer chains. So when we have a nitrogen here and nitrogen from the other side, so they interact and they bring the chains together and they have tighter porosity. and tighter pore size distribution, and thus lower PET surface area, lower permeability, but higher selectivity. Another studies were focusing on evaluating the effect of bromine atoms. So for people that knows like a little bit of chemistry, bromine atom is a bulky atom. It's a halogen. So we decided to study the effect of introducing different types of halogens. Actually, we tried the chlorine and the fluorine, and also compared it with hydrogen. This material is commercially available. This is a synthesized. So once we prepared this, we ran a simulation to evaluate the angle, and we can see with and without bromine, we have the same angle, 105, 104. So it's more or less the same. So any effect will be observed, and the final product will be resulted from the presence of a bromine. So we have prepared the porous polymers from hydrogen-containing polymers and the bromine-containing polymers, and evaluated its performance. And as you can see, if we take this point, this is a fresh material, and this is 1 year aged material. Same for here. This is a fresh, and this is 1 year. So if we look at the fresh material, we can see just by adding a bromine, we are increasing permeability like from roughly 20 up to 50. So we already increased the permeability of oxygen, and at the same time increased selectivity from 4.2 up to 6. And this is very good combination in terms of oxygen permeability and O2N2 separation. These materials is commercially available materials, and that have been used in industries for air purification, oxygen nitrogen separation. So we can see just our material is performing very close in terms of selectivity, like 6 in the 6 and 7 range, and even higher, maybe 10 times in terms of permeability. So we figured out that any change in the polymer structure could have a very significant effect on the performance. So we decided to look into more polar groups. Then we wanted to see what is the effect of COH in performance. So we first check in the literature if there is any PIMs materials prepared from COH groups. So we haven't found any polyamides consisted as a porous polymer and having a carboxyl group. But we found a very common polymer that everyone in the academy, they're trying to use this because it produces very good selectivity of carbon dioxide over methane. So this is performing in this region where we have a permeability of carbon dioxide 11 and selectivity 72. There is another polymer which is not functionalized. So that's also have been prepared and the studies for gas separation, and it is performing in this region here, where it has very high permeability but moderate selectivity. So researchers have tried to develop a new type of copolymer where you mix this one with this one in 3:2 ratio, and you achieve a performance between which has like a good permeability and a good selectivity at the same time. So we thought, why we have to go for a copolymer? Why we just make a new polymer that combines these two parameters, like having COH and having a trimethyl groups here? So we designed this type of polymer. This polymer has a polar group, so we can study it and see the effects of this polar group. And it has the 3-methyl group, so we can compare it to this one as well. So the performance of this material was in the range of at this position here, where it has a permeability of 144 barrier and selectivity of 45. And this is very good combination for industrial approaches, as have been reported by one of the pioneers of gas separation, Dr. Baker, that if you have a material have a permeability around 120 to 140 with selectivity of 40, so this would be very promising for different types of separations. Okay, so why is this happening? What is the function of COH in this group? So why COH is doing such a big changes here in terms of selectivity? So we did some molecular dynamic simulations to see the effect of carboxylic group. And we were able to find that this carboxylic group, it's known for its strong hydrogen bonding formation. So we found that the hydrogen of this COH is doing hydrogen bonding with other COH group, is doing hydrogen bonding with the fluorine groups, and a little bit of hydrogen bonding, which is a weak hydrogen bonding with carbonyl and imide group. So because of this hydrogen bonding, we had a tighter structure that gives at the end better selectivity. So remember, when we talk about higher selectivity, it means it has to be a tight structure, because an open structure will let all gases go through it. Then after this, we said, okay, maybe we just try to check stronger polar groups, because now we know that polarity is having a strong effect. So why not checking a stronger polar group? And we came out with checking the SO3H. So SO3H known to have a very strong polar groups, and even stronger than COH. So we have prepared and designed the polymer that has SO3H in the place of COH. So now we have a comparison about the strength. So we can look at this. This has no functionality. This has COH, and this has SO3H. So before testing the gas separation performance, we checked the fluorescence spectroscopy of these three polymers. So as you can see, the black one, which refers to the polymer with no substitutants, this one has no function groups. So the fluorescence spectroscopy was very minimal. When we add a COH here and get this type of a polymer, and this is the red curve here, you can see like the intensity has increased 2-3 times compared to the non-functionalized. However, when we replace this hydrogen with SO3H and we generate this blue curve, then we have like maybe 5 to 10 times higher in terms compared to the non-functionalized, and 2 to 3 times higher than the COH one. So what does this mean? This means if I have higher fluorescence intensity, then I have something called a stronger charge transfer complex formation. And then we have a stronger chain packing, which is resulted from the stronger interaction between the chains. And thus we have better sieving properties. And if we have a better sieving properties, it means our polymer is going to favor some gases to go through over other different type of polymers. And thus we achieve higher gas separation selectivity. So when we're looking at this, the performance of mixed gas in this case, so we can see these are the place of the commercially available materials. This one is the performance of non-functionalized, which has high permeability and low selectivity. This one has even higher selectivity, but still keeping good permeability. And this one have the extreme, like the highest selectivity compared to the other one that's contain SO3H. Okay, so by doing simulations, we also found that there is a strong interaction resulted from the presence of SO3H as a hydrogen bonding source, where it can form a hydrogen bonding with carbonyl nitrogen within itself, like from different groups and different chains, and it can form like a complex of hydrogen bonding with all of the atoms around. So after we finished these studies, we were looking about industrial approaches. So, you know, for industry, it's always important to have an easy prepared materials that can be scalable, and it doesn't have many synthetic steps. So all of most of the material here that we have generated or we're still generating, it consists of many synthetic steps. So we thought about developing a new type of materials that can provide porosity, and at the same time, it can be easily prepared. So in collaboration with Stanford University, we were able to develop a new type of materials. We called it canal. So canal materials is unique in terms of its morphology. So it is kinked. It's not a planar. It has a W-shaped structure. And at the same time, it's prepared with only one synthetic step to get this unit. So we have prepared the three different types. Also, we have studied the effect of having methyl groups. Again, we go back to the effect of structure-property relationship. So what would happen if we have a one methyl group next to this imide linkage, or two methyl groups next to the imide linkage, or even no methyl groups next to the imide linkage? And we clearly see that the presence of methyl groups next to the imide linkage is providing a strong or higher porosity and high PET surface area. And I think this and having said that, if we look at the performance of this material and we compare it to the commercially available material, we can clearly see that the one that has two methyl groups next to the imide linkage is performing very high in terms of permeability, which is up to thousands. And when we go less with imide linkage, then with methyl groups next to the imide linkage, then the permeability goes less, but the selectivity goes higher. Can you still see my screen? Because I'm having freezing Zoom here. Howra, can you see my screen?
Yes, I can see at least.
Oh, yeah. Well, I'm not sure why it's freezing here. Okay. All right. So those examples were just to show the potential use of porous polymers for gas separation. So now we want to move to a new type of applications and use these porous polymers for organic solvent nanofiltrations. So polyether ether ketone is one of the non-soluble polymers in organic solvent. It has a semi-crystalline morphology, and it's non-porous at all. So researchers have tried to solubilize it in acids to obtain a soluble material that they can use for organic solvent nanofiltrations. And for just a brief idea about organic solvent nanofiltration, so it's a technique that uses to separate the small molecules in the range of 50 to 1,000 or 2,000 daltons in size from solutes, and it's very needed in chemistry, industry, and pharmaceuticals as well. So people trying to investigate to achieve higher permeability and flux for the membranes they develop. So for this study, we looked at this commercially available material, and we found that this cannot be used for high performance polymers. So we thought about replacing this flat unit with kinked unit. So having a kinked unit will generate a porous polymer. So we have selected the three different kinked units, as you can see here, and we have tested these units. We have prepared out of these membranes. So to prepare membranes for SN, it's very simple. You dissolve your polymer and form a DOP solution, and then you cast it, and then you phase invert it in water, and you end up with having a film or membrane for organic solvent nanofiltration. The performance of this new generation was way higher than the commercially available one. So we were able to fine tune the performance in terms of permeance and going like up to 6 times higher than commercially available, while keeping to for some polymers even higher rejection of styrene dimer. So for further investigation, we wanted to see if the molecular weight of this polymer could affect its performance. So we prepared two different types of molecular weights, polyether ether ketone, and we prepared membranes out of it. So the SEM shows very interesting behavior on a polymer that have a low molecular weight. So if we have a high molecular weight membrane polymer, the membrane would show just a flat surface. So as you can see in this illustration or in this SEM. However, when you have a low molecular weight polymer, then there is a kind of honeycomb pattern morphology is formed on the surface. So this is maybe resulted from some aggregations. We couldn't really find why we have it, but we tried like with low molecular weight, different concentrations, different parameters, and we're always getting this honeycomb morphology. So the presence of this honeycomb morphology led to enhance the flux and the permeability of the solvent and had better performance than the flat surfaces. However, so when we talk about organic solvent nanofiltration, it's important to consider that the membranes we are using is stable in organic in organic solvents and acids. So these are somehow stable in a specific type of organic solvents, but still some polar aprotic solvents like NMP can dissolve it easily. So we wanted to enhance the stability of these type of materials. Then we thought about cross-linking. So cross-linking is well-known as strategy to enhance the membrane stability, but it has some requirements. So to cross-link, you have to have some function groups that will be able to do the cross-linking. So we have selected the nitrogen-containing IPIC polymer that we have developed in previous studies, and we cross-link it. But we wanted to have a different way of presenting a cross-linking because we believe that having a cross-linking with a normal cross-link could give you a normal results. But what will happen if we change the stereochemistry of the cross-linking or even the size of the cross-linker? So we thought of taking 4 cross-linkers with para substituents. So this and this are para. This one is 1 ring, this is 2 ring. This is ortho substituents. So here we have changing stereochemistry between para and ortho, and also 1 ring and 2 rings. So by calculating the distance between the function groups, we can see we have different ranges in terms of the sizes. So we found out after testing and analyzing this material that the cross-linker is playing a very important role in determining the performance. So if you use a longer cross-linker, that will make more space between the chains, and thus you have a higher flux and higher permeability. If you use a para, it will be giving also higher flux compared to ortho. So we generated this curve to show if you want to select a cross-linker for this type of materials and for this specific application, which could be applied also for other applications, you could look onto going from 1 ring ortho to 1 ring para. For example, this 1 ring ortho and this 1 ring para. So if you take this one instead of this one, you have enhancement of 15% in flux. However, if you go like from 1 ortho to 2 ortho, which means 1 ring ortho to 2 ring ortho, you have around 60%. And the highest increase in flux was achieved if you try to go from change your selection actually from 1 ring ortho, from having this one, and go to this one, where you can make 120% increase in flux. And this also was like way better than the commercially available material that used for this kind of separation. So having mentioned the importance of peak, we thought also because there is no study about the degree of sulfonation, so this is not really related in for porous polymers, but I just want to go through it quickly. That is very important to know the effect of degree of sulfonation on the performance of the material. So it doesn't mean that if you have higher degree of sulfonation, so you have higher degree of absorption or you have better performance. So we have generated from experimental data that this curve that shows at up to some point, when you increase the degree of sulfonation, you're still getting higher water uptake and higher performance. But after that, it starts to go down. And to explain this, we did a simulation. So where you can see if you have a polymer, like this polymer, consisting of SO3H. So if you increase the number of SO3H up to 20, all of the SO3H will be able to interact with the motor molecules from outside. However, if you go higher up to 30, 40, or 50, then we will have internal interactions of SO3H between each other, and they will be busy interacting inside rather than interacting with water molecule. And the curve generated here is resulted from the distance between S atoms. So when you increase degree of sulfonation, the SO3H's are far away from each other. But at some point, they start to get closer, closer, and very close when you have very poor performance. So this also flies in the structure property relationship to better understand how the material is behaving. We also decided to find out some applications for PIMs for oil industry. So water and oil is a common mixture when you talk about reservoir. So it would be good to develop some material that can purify or treat this water. So we have used the polymers of intrinsic microporosity, but we've generated a different type of membrane, is known as a nanosheet and made from electrospin fiber. So the process of preparation is going through electrospinning. Then you generate this fiber where it is nanofiber, but it has meso and micropores inside, resulted from the microporosity of the polymer. And this is how it looks like. It's very like white material, foldable easily, and this is under the SCM, the fiber is how it's packing. So it is macropores, mesopores, and micropores at the same time. So we have used this to separate water from oil and toluene, silicone oil, metaxylene, crude oil, diesel, and gasoline, and it performed very well. And you can see here, like by looking at these figures, you can see here we have a oil on the top of the water, and once we throw this membrane on the top of it, then all the oil will be attracted to this membrane, and we have a clean water afterwards. So this one applied application, which is also could be interesting for environmental friendly applications. Another applications we thought of is using polymers of intrinsic microporosity for volatile organic compounds removal. So that there is lots of gases and volatiles organic goes into the air and it form a polluted air. So the principle of this work is in this illustration where you have a polluted air and then you have a fiber mat or sheet, then prepared from porous polymers. Then the air goes inside, it goes through it, and it purifies it. And also we incorporated metal organic free work to see if this could have any potential enhancing in performance. So we tested formaldehyde, toluene, xylene, and methylene, and we figured out that we can use PIMs by itself without incorporating this, and we're achieving almost the same performance. So this is almost the same. This is almost the same when we have MOF. This is almost the same, and this is exactly the same. So MOF is not playing a role in highly porous polymer, but we can see here, like when we put MOF in non-porous polymer, so it increases it. The direct application, we wanted to see if we can electrospin these nanofibers on the face mask, because we can apply this for the region that is highly polluted, the air is highly polluted, so we can apply a face mask coated with these type of polymers. And we were able to, as you can see in the SEM, to integrate and add this polymer on the top of the face mask for VOC removal. And the last application, which is not very related to oil, but it's also a new application in OSN I would mention, is using PIMs as incubators. So for electronics, there is a type of quantum dots and perovskites generated, and it's like one of the most promising material for the future. So they have a problem in terms of air sensitivity. So it's highly air sensitive, and it could decompose fast. So we thought of putting these nanocrystal inside our polymer. So our polymer is a porous polymer. Then why not just make a membrane and put these nanocrystals inside? So this image is a high resolution TEM. You can see the blocks of the nanocrystals without the polymer and the blocks of the nanocrystal with a polymer. So almost there is no change. So the polymer was integrated here and didn't affect the arrangement of these nanocrystals. So after looking at the performance, this material was without a polymer. It had around 70% reduction after 7 days. and it continued decreasing. However, after putting a polymer, we have only 20% reduction, and it stops decreasing like after 5 days. So from 5 days to 7 days, there is no change at all. And this is kind of a promising for different future applications. Having said that, I would like to thank Hawra for arranging this webinar and for the invitation as well. And also would like to thank the professors and colleagues that I have worked with and contributed to this work. And I'll be happy to answer your questions. Thank you.
Thank you, Dr. Mahmoud. شكرا دكتور، شرفتنا ومشكورين على هاي المحاضرة الممتعة.
شكرا لك. Any questions?
طلاب، أي شخص عنده سؤال يقدر يكتب بالشات. الظاهر دكتور ماكو أي سؤال. مشكورة كلش على المحاضرة هاي الجميلة اللي ألقيتها. مشكورين.
شكرا. Have a good day.
شكرا.